And yes, with this, the floor is yours, Aleksandra.
Thanks so much for the great introduction. Thank you for inviting me. And I'm sorry I couldn't be here with you in person. I'll take a rain check and next time I'll see you in person. So I want to talk about some of the recent work on scalable autonomy and autonomous systems and agents. But before we kind of go there, let me start with a question. Do you happen to have a relative or a friend, or maybe it's even yourself, that struggles to complete everyday tasks that most of us take for granted? Maybe it's difficult to read text on the screen. Maybe the buttons are too small, or a mobility impairment makes it challenging to leave home. 15% of the world population, or 1 billion individuals, live with some sort of disability. That's a lot of people. Autonomous agents in all shapes or forms, from the autonomous cars, service robots, and even these digital assistants that we really don't think of the robots, but they're really bots there, have a tremendous opportunity to improve the quality of life and independence for millions of people. So what does that mean? Let's take a video here. We really need to get autonomy at scale. And what does scale mean? Here we have a robot that's trying to do the same task, go from point A to point B to the faucet here, to the sink. And it's dealing with whatever comes along the way. So there is a person here now needs to adapt and kind of go around. This is one aspect of the scale. Scaling to different environments and dealing with whatever needs to be dealt on the ground, messy stuff, and so on. And this is really not staged. Now there's a custodian coming in here. This robot is taking observations via its sensors, LiDAR observations in this case. This is a fully learned reinforcement learning policy that outputs linear and angular velocity. So this is one aspect of the scale. At Kino, we're not quite there. And we typically tend to train the agents and ask how to transfer them to real world. Instead, I suggest we shoot a different question. It's how to effectively train agents that bring joy to the end user. Now, to me, to understand that answer to that question is what scalable autonomy means. Joy is not a technical term, I'm putting it here on purpose, and carries a lot of weight here. It encapsulates anything from agents' performance, safety, to building user trust, and so on. And we have rich body of questions that really, or work that covers these areas. And kind of deeper that are not specific to any robot type or a system. So let's look at kind of several examples here. One kind of go over some of the recent work. First, go under cold conditioned anywhere policies that we're looking at robot going from A to B, like I showed in the video, that need to deal with environment generalization. So we need to have a same policy that kind of generalizes across the environment. And then follow-up work to that is how to do that in a socially appropriate way to find the sub-goals working with humans when humans are really on the scene. And then move on to next aspect of the scalar tasks and multitasks. And one step further, how do we go from multitask to the emerging complexity? So how do we get trained to robots to actually start doing more and more difficult tasks instead of just kind of fixed set of tasks? And finally, the fourth aspect that I want to touch on today is that if we want to have robots or bots working with people, along the people, they need to communicate. So how do we go about learning relevant communication? So to learn, this is the video that I showed earlier. How do we train an RL agent that goes from A to B? I mentioned what the observations are. The problem here, one of the problems here is the reward. Reward is reach the goal. It's a goal condition. It's a sparse. That's not generally easily trainable. We do have a good intuition here what the features of the rewards are. Distance to the goal, orientation, speed, and whatnot. So we can have a parameterized reward that then we can learn with respect to the task objective, which is reaching the goal. So we do that with training population of agents, initializing rewards randomly, training each agent, evaluating with the task objective within task objective, which is the reaching the goal or not, and then having the mutator that proposes the next parameterization. And we repeat this loop 1,000 times and end up with a reward that's really tuned to the task that we're trying to solve. Then the second loop, we freeze the reward and learn the neural network architecture. In this case, it's very simple, the width and the length of the networks, but we kind of go from there, and this time we evaluate against the cumulative reward because that's fixed. And that produces really policy that performs well. The training is in a very simple environment like the one shown here with no moving obstacles and whatnot. We do add lots of noising and domain randomization in noise to the sensors, noise to the kinematic model, noise to the action model, everything that can be noised up, we noised. And we find that that brings the robustness. So policy trained this way does a zero-shot transfer to real world that I've shown earlier in the video. And it works on a variety of the robots at the same time. So to have the policy, the consistency does generalization across the environments, two things. Noise during training creates robustness, and learning to learn improves the performance. Now, next question is, what do we do when there are people around? How do we possibly train robots around people? Doing it on a robot is difficult. Well, first you have representation issue. How do we have enough humans who are volunteering to solve this? There are ethical concerns around it and safety. And then there is also a question of safety. So we opt to do it in simulation and combine two different data sets. The one is the photorealistic Stanford large data set of the 3D indoor environments. And in it, we superimpose a real data set of humans, which are synthetic humans, and we equip these humans with different behaviors, behavior policies that they can follow. And also we can vary their gender, texture, to be clothing, skin color, facial features, body shape, and so on. And now we have the environment, generative basically environment, that you can generate many, many different scenarios. And here is an example of what that might look like in different settings. So now that we have this environment, we can generate a data set, basically randomly initialize the environment, use something like MPC to roll out different scenarios and collect a data set. And we observe, basically we want to find what is the sub-goal here. So for every sub-goal that we accepted, we kind of say, hey, at the beginning, this is my sensor observations, and here is the cost associated with that sub-goal. From there, once we have the data set, we train a predictive model that associates image, waypoint, and produces the cost predictor. Once we have that model in the planning phase, then we sample the candidate waypoints and estimate the cost and select the cheapest. And then we look in the first, and then we transfer to the real world. So we do see that this model actually recognizes when the human is static, it goes in front of it. When the human is moving in the direction, it goes behind the human. And we're thinking that associates the leg positioning actually with the motion, which is kind of cool. We also see that the baseline, which was trained without humans the same way, actually cuts off human in front. This is the dashed line, whereas the model trained with the humans goes behind it. We also observe that even though we train with a single human, the model has some ability to handle multiple people on the scene. And then when it's transferred on the robot, and there is difference here, the camera in training was 60 degrees field of view, this one is 45. It goes and avoids the person and finds the goal. So there is something to be said here for safe and private training, which is a challenge in these realistic settings and scaling up, is that the photorealistic environments in synthetic humans have a promising direction. Next I want to talk about is the emerging complexity. And for this, I'm going to shift out from robotics for a moment into autonomous web navigation. So I want to ask when we do many things on web, food ordering, change your password, I don't know, purchase something on the website, we're able to do that task without additional training. And these are called form filling tasks. It is essentially mobile manipulation task. We manipulate the field to enter our first name or our address, right, and so on. We complete things on a page, ignoring things that we don't care about, like ads and whatnot. Then we go and find that submit button that takes us to the next page. You can kind of think of it as a door in navigation environment that kind of brings us to the new room, right? Where there's like a whole new manipulation set of tasks that we need to solve before going there. The environments are noisy, just like in robotics. You can think of it as different elements, ads and whatnot, pictures, images, changing positions like a furniture changing in the robot manipulation, right? So, but there is no embodiment. So it's kind of easier to study multitask learning in this setting. And we want here a single agent that solves any task in this class of the form filling tasks. So zero-shot transfer. Like in robotics, we can't train it easily on the real websites because we can't buy a million iPads or million movie tickets or airplane tickets. The commercial flight booking websites are huge, 30,000 DOM elements on them, whereas the existing benchmark before we did this work had about 100 DOM elements. So it was very, very simplistic. The existing methods before we did this was agent that solves a single task in this simplified environment without generalization to different environments on different tasks and requiring millions of samples. So we're after agent that can do this multitask in realistic settings and whatnot. The observation for the agent are HTML. Take the DOM element because that's the observations in a natural setting for this agent. And the action is give me an element and a value to put in it. So it's a discrete action space and it's huge. A task is given as the profile of the user, so all the information that needs to be done and the entry page that needs to be solved. So basically needs to solve this combinatorial aspect of it. So first observation here is that we can kind of think of this web navigation and form filling as really compositional tasks, where these manipulation tasks are primitives, things like fill in the first name, fill in the date, and then the date can be either a select on a calendar or type in, or I don't know, select gender, which can be a drop down or a radio button and so on. So these are the primitives that the agent can have. And then tasks are combination of the primitive tasks that the agent needs to do, put in several pages that are connected through the submit button or kind of the narrow passage that it needs to pass. So first thing first, we put a benchmark, basic environment in the benchmark, which we call gminivob, that creates compositional tasks for the websites, mazes, and mining. So on the website is precisely what I just described, primitive objects, go to pages, go to page transitions. And for mazes are things like, I don't know, pick a key and then go to the door, or kind of several of these things. All right, so now we have environment where we can generate the tasks. How do we go about training? These are very long horizon tasks and large action and space and observation spaces. So what do we do about it? Curriculum. So we propose compositional design of environments method. It's basically we're going to co-train a curriculum agent and a population of the RL agents. So what we call designer, it's an LSTM that is a decoder for compositional tasks. Its job is to produce just the right challenge or just the right environment for the navigation agents. And here is an example of the LSTM rolling out a web page or a series of the web pages. It starts with how many pages it's going to do, and then which element it's going to put on which element. That's kind of the decoder task. That environment is then presented to a population of RL agents in this case, that kind of collect some experience and train from it. And then after an update, the designer LSTM looks at two things. It has a two-piece loss. One feedback is what is the performance of the best agent, and what is the range, or kind of approximate regret is the range of the performance of the agents. And these two signals, mind you, designer does not care how they were trained, whether it's RL, imitation learning, humans don't care, right? So the best agent performance gives a signal, is this too difficult or too easy? So if the best agent is performing well, means that this is an easy challenge. Let's kick it up a notch and add more design elements, more pages, and make the environment complex. If it's not doing well, then it's too difficult. Let's kind of take it down. The second signal is this regret, which basically shows the range, and it kind of helps LSTM decide what elements to pick. If nobody's solving the task, that might mean that the task is not solvable, so maybe we need to kind of put different elements. If there is a good range of the performance, that means it's an interesting thing that the LSTM selected, so yeah, continue that. And then we select, then once the agents are trained, we evaluated in hand-designed, not before seen environments. So what do we see? We see, not surprisingly, that environments become more complex during the training. So very early on, we have very simple web pages. Late in training, they have many elements and multiple pages along with it, which is kind of neat to see. The second thing, we see that agents do generalize to unseen environments. The blue line is performance of our agent. Red line is paired, which kind of only contains the regret loss, but not the difficulty budget loss that I mentioned. And then green line is the manual curriculum, where we kind of try manually to vary the difficulty of the agent. And then third thing that we notice, that the distribution of the primitives that the LSTM or the designer selects shifts towards task relevant elements later on in the training. So early on, it's pretty much uniform distribution. Later on, it starts actually creating the picking out the elements that are needed for. So if you just have a web page that only contains images that are not completing tasks, well, that's not a good website. What's interesting, though, is that these are not semantically correct websites. First name can appear 15 times and so on. But as long as there is some form filling, that's a valid task to solve. So the question here is, does it work in reality? To test that, we select 3,500 primitives scraped in from the web, which kind of induces the task space about 10 to the power 31, which is huge. Most of these are from the login tasks, and we evaluated on our benchmark that we proposed. And we see that on the login task, it actually performs like 60%, whereas on the other tasks performs worse, which is expected. But then when we evaluate that model within domain from where it was selected, it actually performs 95 plus accuracy rate in kind of predicting the right things. This tells us that the benchmark that we have out there is verified on the real commercial websites, and it's difficult enough. It's open source, it's out there to be used. So the key here to kind of making this compositional emergent complexity is finding the right challenge for the agent to train. Last, I want to briefly mention is around relevant communication. In this case, we have a visual navigation task. We want an agent that is presented, that's presented with a path or a video of a trajectory to create natural language instructions for humans that humans are able to follow and execute. Prior work found that it's tricky to do that. The instructions that are created are creating landmarks, or kind of mentioning landmarks that humans are not able to follow. So it works in 3 steps. We learn the landmark extraction, then we learn landmark detection, and then final instruction generation in this case. So to get the landmark extraction, we ask annotators to speak while traversing the paths. So we end up with 100,000 instructions that are temporal. So we have the instruction that is time associate with the videos that where the human was when it mentioned certain things. From there, we extract the keywords with MBERT model, and then ground them within the images to find exactly the landmarks where they're likely the most relevant first time to be mentioned. And out of that, we extract close to 1 million landmarks description in English, Hindi, and Telugu languages. Next step then is to find the landmark detector. So if we have the 360 panoramas, we output the bounding boxes. The model outputs the bounding boxes of the relevant benchmark landmarks that we selected. And it learns basically once we have that predictor that's trained on the data that we just extracted, we can generalize it to the unseen environments. Finally, when we do instructions, we have a template that's kind of replaced with the images of the extracted landmarks. And for the MT5 prompt, translate placeholder template to English, Hindu, and Telugu, we get realistic instructions. And here is an example. What's interesting here is that if we differently sample landmarks, we produce very different instructions, which is really cool. And the results are pretty exciting. It virtually closes the gap with human instructions. So in never before seen environments, the model is able to extract the instructions that are human navigable. And the key here is really to use this weak supervision on a little bit of the data for humans to tell us what are relevant and visible and feasible landmarks at the time they are, and then generalize from there. So went through 4 things here. The first one was how to do the environment generalization well, and how to address robustness and performance. Then the 2 second ones are there is evidence that the generative models and generative environments play a role in generalization, socially appropriate and emerging complexity tasks. And finally, for the communication, using a little bit of the weak supervision data and then unsupervised extraction and whatnot to get the landmarks and the items that are relevant to the end user are some promising. There is a lot more to be said. Again, I want to emphasize the area is huge. There is tons of potential how to do this responsibly and how to scale up autonomy and kind of look at these kind of fundamental topics. One thing that I'm thinking a lot now, we know that the data plays and environments play a huge role. We also know that methods play a huge role. What is this fundamental trade-off? When do we know to invest more in data and environments versus more in methods and loss functions and neural network architectures and so on? How do we quantify that dependency? Is something that I'd really like to see answer in near future. But without further ado, I want to thank you. I want to thank my collaborators. Here are the links to the paper and the open source code for.
Thank you very much, Aleksandra. That's